Welcome to the Advanced Fluorescence Microscopy and Image Processing course. So today is lecture 13 and we will discuss about digital images and camera technologies. So as you know, until now we have discussed about various parts of a microscope, starting from various types of light sources, various fluorescent filters, and various types of objective lenses. Okay, so detectors like the cameras are also very essential for capturing uh, high resolution or good quality images. Okay, so that's why today I will show how to select the best camera for your microscope. Okay, so you can see here there are mostly one of these three types of detectors present in microscope. So either your microscope is equipped with CCD or EMCCD type camera, or SCMOS type camera, or if you are using a confocal microscopy, then the photomultiplier tube is used as a detector. And I will explain that why in confocal the photomultiplier tube is used, whereas in other imaging technologies the camera EMCCD or SCMOS camera are used. So EMCCD stands for electron multiplying charged coupled device, and SCMOS stands for scientific complementary metal oxide semiconductors. Okay, so I will explain you how this different cameras, which kind of different technologies they use in the next class. But today we will discuss mostly on the digital images and different types of camera technologies. So here I have shown a chip of a CCD camera. Okay, so if you see, this chip looks like this. Okay, this is the same chip like your mobile camera are using. Okay, so it's a CCD camera chip and it looks like this. If you see it under the microscope or you zoom it, you can see this kind of pixels. Okay, so basically the CCD camera chip can so each pixel can be classified with different numbers. Like this is the pixel known as 0 and 0, because in X and Y position it is at number 0, whereas this pixel is known as 9 by 9 because it is at this position. Okay, so each pixel can be defined by a specific number, and CCD camera chip is made up of this kind of pixels. And many times we hear about the megapixel of the camera, right? So what is a megapixel? So see, the higher the pixel counts, the greater the density of the pixels on the sensor. So what does it mean? For example, a camera with 1600 by 1200 pixels equals to 19 lakh 20,000 pixels, and that is divided by 10 lakhs, and that is equals to 1.9. So this is considered as a 2 megapixel camera. Okay, if you have the chip camera chip of 1600 by 1200 pixels. Okay, so 1600 pixel this way and 1200 pixels this way, then that camera chip is known as 2 megapixel camera. So basically the megapixel represents the how many number of pixels are present on the camera chip. Okay, let's say this is the camera chip, it is 9 by 9, so 81 pixel camera. Okay, but similarly generally the CCD or EMCCD camera have so many pixels, and they are known as 2 megapixel, 5 megapixel, 8 megapixel. So depending on the number of pixels available on the chip. Now what this pixel does? Okay, so see, this is a pixel, and what is the function of this pixel? So pixel converts the photons into electrons. Okay, so from where these photons are coming? So these photons are coming from the fluorophore on your sample. So let's say you are visualizing the GFP tagged protein. So GFP tagged protein will emit the green color light, and that is a light. It contains photons. Those photons hit the pixel, and this pixel will convert these photons into electrons. Okay, and that efficiency is known as quantum efficiency. That how many photons are getting converted into electrons. So let's say if there are 100 photons are hitting the pixel, and this pixel is converting 100 photons into 95 electrons, that is known as the quantum efficiency of 95%. Okay, generally the cameras which are used in microscopy today, they are generally having the quantum efficiency of 95%. That means they are converting 95% of the incoming photons into electrons. Okay, and these electrons will be recorded by the computer or your software in terms of the grayscale, that how more the electrons, more the bright pixel. Okay, so this is how the image is formed on the computer screen, because camera pixel collects the photons coming from each area of the sample, and it converts photons into electrons, and those electrons are recorded pixel by pixel. So what computer knows, okay, at this 0 by 0 pixel there are only 5 electrons. Let's say in this 9 by 9 pixel there are 50 electrons. That means this pixel is brighter, 10 times brighter than this pixel. Okay, so computer knows the electron counts of each of these pixel. So what is a digital image? So here you can see this is just a digital image made up of black and white color. Okay, and how the computer sees this image. For computer, the white pixel is known as, is given the intensity value of 1, and the black pixel is given the intensity value of 0. So computer knows this image in the format of 0 and 1 only. Okay, so wherever the white pixel is there, it will put the value 1, and wherever the dark pixel is there, it will put the value 0. This is known as the 1-bit image or the binary image because it has only two shades, black and white. Okay, so this is known as 1-bit or the binary image because of having only two shades, and it's easy for computer that there are only two values, either 0 or 1. There is no intermediate values. Okay, but in real camera, it does not work like that. So this is what we see in the microscope or microscope image, right? And you see that some of the parts are bright, whereas some of the structures are low in intensity. Okay, so how camera records this brightness? So as I mentioned, that pixels are numbered like x1 y1, x1 y2, x1 y3. That way x9 y42. All the pixels are numbered like this, and computer knows the electrons or the photons coming from each of these pixels. So this first pixel is having highest number of electrons, 200 or maybe 200 electrons. This pixel has the highest electrons, 201 electrons, and this is the pixel quantization. Okay, this is a pixel wise fluorescence intensity or the number of photons that are converted into electrons, that data. So this is how the computer sees this image. Okay, but on screen it is displayed like this. So this is known as a digital image. Okay, here is another example how to reconstruct the image. So the image is reconstructed or is generated by the reconstruction of the pixel val information, now digitized into grayscale values into the image pixel. Okay, so as you know, if this is a human face, okay, but computer cannot see that this is a human face. It just knows that this pixel is dark, this pixel is bright, this pixel is having intermediate gray value. Okay, so it just knows the number for each pixel. And you see, so the this is, let's say this is the brightest pixel, so its value is 237, whereas this is the darkest pixel, so the value is 0. Okay, so it is here there are multiple grayscales. See, this is not a binary image or the 1-bit image. Okay, here there are multiple grayscales, and by looking at these values, I can say that it's a 8-bit image because it is having 256 shades. Okay. So now the question is, can your CCD camera see the color? Let's say in your mobile camera, you are getting the images like this. Okay. But can your CCD camera see the colors? The answer is no. Your CCD camera cannot see the colors. Okay. But how it produces the color image? So here is the reason that how CCD camera can produce color image without actually recognizing the colors. So each of this camera pixel is layered by a Bayer mask. Okay, so this is known as Bayer mask. So each pixel of the CCD array is permanently bounded to a red, green or blue filter, and software interpolates color contribution from neighboring pixels to deliver color estimates for each pixel. Okay, so what happens, let's say whatever the pixel is coated with this kind of blue color filter, so only it allows the blue light to enter. The pixel which is coated with green color filter, it only allows the green color light to pass through, whereas the other wavelengths are stopped. Okay, and the pixels which are coated with red color Bayer mask, they allow only the red color light to pass through. Okay, so this way each pixel only quantifies one particular wavelength, and then the software interpolates that data and makes the color image for you. Okay, so basically the CCD camera cannot see the color. It just measures the number of photons coming per pixel, and because of the Bayer mask allows only one wavelength to pass through. So only the one wavelength can hit the pixel, and it can convert photons into electrons. So this is how the color images are produced. Now, generally in microscopy, the color cameras are not used. Generally, the monochromatic cameras are used in microscopy. So the question is, why color cameras are not used? Why the microscopy cameras are not, the chip of the microscopy cameras are not coated with that Bayer mask? Because, see, generally for imaging biological samples, we need the quantity information, that how much protein is expressed. For many applications, we need to quantify the fluorescence intensity of different fluorescent proteins like red, green, and blue. Okay, so if you capture the monochromatic image for each color, then you can actually quantify their intensities. But if you produce the color image with the Bayer mask, then the individual fluorescence intensities cannot be quantified with accuracy. Okay, and that's why our purpose is the quantification, not only the good visualization. And that's why we use the monochromatic camera, and also we take the image sequentially. Let's say if we have to image three color sample, red, green, and blue, let's say first we'll image the red color, then we image the green color, then we image the blue color. Okay, so we take the images sequentially, so that we can adjust the brightness and intensity for individual channels, and if you want to measure the fluorescence intensity of each color, that we can measure. And that's why generally the monochromatic cameras are preferred in microscopy over color camera. But you will still see some microscope equipped with color cameras where the application is not that much on quantitative measurements, but the application is based on just visualization of different colors. Okay, then people still go for the color camera in microscope. Now I will explain you a couple of terminologies which are being used for taking images by camera. Okay, so many times we discuss that the bit size of the image. Okay, so what is a bit size? So let's say this is a 1-bit image, so it has only two shades, black and white. Okay, then this is a 2-bit image, so it has 4 shades. Okay, and this is a 8-bit image, so it has 256 shades. Okay, so basically bit size represents the shades of the gray value. Okay, a picture can display. Okay, so bit size is expressed as 2 to the power n. So 2-bit image is equals to 2 to the power 2 is equal to 4 shades. 8-bit image is equal to 2 to the power 8 is equal to 256 shades. Okay, so let me show the next slide. Yeah, so here you can see how different shades can be represented with respect to the bit depth. So if it's a 2-bit camera, it can represent 4 shades. Okay, so this is the bit size and this is the number of shades available. So it's for 2-bit image there are 4 shades. For 10-bit image there are 1024 shades. For 8-bit image there are 256 different gray values. Okay, so this is known as the bit depth. Generally these days in microscopy, even most of the cameras are even more than 10 bits. They are generally 12-bit or 16-bit cameras are used. Okay, so many gray levels are there, and better the bit size of the camera, more will be your image size. Okay, so size of the image will increase. Size in terms of the amount of space it occupies on your hard drive. Okay, so let's say if you capture one image with a 6-bit camera versus you capture the same image with 10-bit camera, obviously the image file size will be more for the 10-bit image compared to the 4-bit image, because here it has to remember more gray values. Okay, and more information. So for quantitative analysis, higher bit size is important. So what is the bit depth? So depending on the camera used, each pixel can carry from 1 to 32 bits. Okay, for a normal 8-bit monochromatic camera, each pixel has a possible 256 grayscale values. So that means the black pixel is represented by 0 and the white pixel is represented by 255. For a 12-bit camera, the black pixel is represented by 0 and the white pixel is represented by 4095. And for a 16-bit camera, the black pixel is represented by 0 and the white pixel is represented by 65,535. So there are 65,536 grayscales can be represented in a 16-bit monochromatic camera image. And these days, most of the advanced microscope which are generally used for the highly sensitive and highly quantitative applications, they use the 16-bit camera. Okay. Now here is an example of bit depth in real life. Okay, so how many different gray shades our human eye can see? So the human eye can accurately detect around 40 to 60 gray levels. Okay, so 40 to 60 gray levels, that means we can, let's say this is 64 gray levels. Okay, so we can see up to 6-bit image. Okay, we cannot see this many grayscales like 10-bit or even 16-bit, but we can see up to 6-bit. Okay, 8-bit cameras detect 256 gray levels, and each gray level captured will be accurately repeated by the monitor display. And 12-bit camera generates 12-bit images. This contains 4096 gray levels. And here you can see the 12-bit scale gives far greater ability to capture the dynamic range. This allows you to extract your data from a larger range. Now, the most important point is here. You see, this is what the human eye can see, 64 gray levels. That means around 6-bit image. Your computer screen can display 256 gray levels, like 8-bit image. Okay, and if you are using 12-bit or 16-bit camera for a microscope, okay, it can see 4098 or even that 65,536 gray values. Okay, but when you are seeing this image on a computer screen, computer has to convert those 65,356 gray level information into 256 gray levels to display that image on your computer screen. Okay, so computer screen, even your camera is very good of 16-bit, computer screen cannot represent that many gray levels. Computer screen can represent only 256 gray levels, which are equivalent to a 8-bit image. Okay. So simple question, that what is the bit depth of an RGB color image that has 3 8-bit monochrome channel? Okay, so suppose you are seeing an RGB image, that is a color image in red, green and blue, and each color was captured by the 8-bit monochromatic camera. Okay, so what is the bit depth of that image? So the answer is 8 into 3, because there are 3 channels. Each channel was captured with 8-bit camera, so there are total 24 bit information available in that image. So many grayscales for different colors are available in that image. Now coming to another terminology that we frequently use in microscopy or while image processing, the dynamic range. So what is the dynamic range? The range within which the darkest and the brightest pixel in the same image can be taken without the brightest pixel being saturated. Okay, so look at this image. I can explain you this phenomenon by showing this image. So this is the saturated image and this is the non-saturated image. Now why this is saturated? Because the camera exposure time was set in such a way that this kind of very bright pixels, maybe the light of the daylight, okay, it is actually saturating the pixels. Okay, and that's why you cannot see the detail on this ceiling in this image, whereas here the camera pixels are not saturated, so you can see these structures also well, means you can see this color of the sky also, and also you can see some details on the ceiling of this image. Okay, ceiling of this corridor. So always while capturing the image, you should make sure that your camera pixels should not be saturated with overlight or over photons. Okay, and what in other way, what do I mean by the saturation of the camera pixel? So saturation of the camera pixel means your pixel is hit by so many photons that it cannot actually convert so many photons into electrons. and that depends on the bit size of the camera. Okay, so always you have to make sure that you do not overexpose your camera pixels. So adjusting the camera bit depth for display. Okay, so you may see that your computer screen can visualize only 256 grayscales. Okay, that means the 8-bit image it can uh, produce. Okay, but let's say your real image which was captured from the microscope, if it is having 4096 gray values, okay, then your screen will convert those 4096 gray values into 256 gray levels to display that image on your computer screen. Or the second option is scale down some gray levels for display or auto display and scaling. So when you generally in the software, it gives you the option or one button which you press for the auto exposure or auto display. So what it does, it only represents the bright pixels and it stop representing the dark pixel. Okay, so there are two ways the computer image can be formed from the real microscopic image. So here I can show the real practical applications of this adjusting the gray levels. Okay, so see, this is an 8-bit image. Okay, so it is having 0 to 255 gray values. Okay, now as I mentioned that the computer screen can display only the 8-bit, like 256 gray levels only. Okay, so this is 8-bit image captured by the 8-bit camera, and it is I'm opening this image on the computer screen, so it is not doing any reduction in the bit size. Okay, but you can see now all the pixels are displayed here. Okay, here 0 represents the bright pixel and 255 represents the dark pixel. Okay, so now you cannot see the structures because all the pixels are being displayed. But now what I will do, I will change this the maximum pixel value to only those pixels which are showing some bright signal. Okay, so now you can see the structures in this image. Okay, so if I now I'm displaying, so this image has all the information of all the 256 pixel, but I asked the software to display only the bright pixels. Okay, so see, it is displaying pixels only up to this point. Okay, so only the bright pixels are displayed, and that's why you can see the structures. But if I ask it to display all the pixels, then it will not display the real structures present in the image. So this is how you should adjust the camera bit depth for displaying your microscopic images. So let us move on to the next slide. So here the same thing I have shown, like if the 16-bit image displaying all levels at once. So 16-bit image has 0 to 65535 grayscales, and all the grayscales are displayed, so you cannot see the structures. But when you display only the first 1000 gray levels, then only you can see the structures. The same thing that I showed you in the previous slide. So in most of the softwares, you will see there is an option of auto contrast or histogram clipping. Okay, so I showed you that histogram. This is another display of the same kind of histogram. So see, it is displaying the value from 0 to 255 on the x-axis. Okay, so 0 to 255 are the total gray level present, and when you keep this triangle here, all the pixel values are displayed. Okay, but only this many are the bright pixels. Okay, so when you push this triangle from this end to this end, then only your all the pixels or your structures will be visible in your image. But when you ask the software to display all the pixels, all the gray levels, then it will not show your structures. So to see your structures, you should always push this triangle to display only the bright pixels. Now coming to the another terminology, which is known as signal to noise ratio in fluorescence spectrum. So what is the signal to noise ratio? So see, the same object you are seeing with different background, right? Different intensity of the background. So let's say this image where the signal to noise ratio is 1.05 was captured with 20% light intensity. This was captured with 30% light intensity. This was captured with, let's say, 40% light intensity. And this was captured with, let's say, 80 or 90% light intensity. So you just increase the fluorescent light and then you will see better signal to noise. Okay. So ideally, if you have to image this sample, you will say that you should always go for the high SNR, like 23 or even more if you can achieve. Okay, but that is not always true, because for visualizing the images like this, you will keep your laser power or the light power or the exposure time high, okay, to increase the signal to noise. But that will also create lot of photo bleaching and phototoxicity. So if you are working with live samples, phototoxicity is a major concern. Okay, so it's not that always you should go for the highest signal to noise, but for any software based automatic detection, you need a minimum signal to noise ratio of 5 or more. Okay, so ideally it is not a good idea to image your samples by keeping the SNR of 23. Instead, use the light just sufficient so that your signal to noise ratio will be 5 or more than 5, like 6, 7 or up to 10. Okay, but don't image by keeping fluorescent light or using a higher exposure time, so that your signals to noise ratio will be too high. It will create unnecessary photo bleaching, and it will not give you any additional information. But if you keep the SNR greater than 5, then the software based automatic detection of the object, which is known as image segmentation, that we are going to cover in the image processing class. So software can automatically see your structure. It can detect different structures automatically if the signal to noise is more than 5. Okay, so it is ideally recommended that you should adjust your fluorescent light intensity as well as the exposure time in such a way so that your signal to noise ratio will remain at least 5 or slightly above 5. Okay. Now coming to the noise of the digital camera. Okay, so what is a noise? So let's say, suppose this is your camera and you are keeping the shutter off, okay, and then you are clicking your camera, okay, for capturing the image by keeping the shutter off. So ideally you expect this kind of image, completely dark image, because there is no light entering from the shutter. Okay, so ideally you should expect this kind of a black image, but instead you will get this kind of noisy image. And why this noise? From where this noise is coming? The noise is coming because of the electrical component present in the camera. Okay, and this noise is unavoidable. Okay, so even there is no other way. Even if you put this camera in the dark room and then you capture, this noise will always be there because of some of the electrons produced by the camera chip. Okay, so I will explain. There are three different types of noise associated with camera that we will discuss. So noise of the digital camera. So there are three types of noise known as short noise, dark noise, and read noise, and how they are correlated. So signal to noise ratio is equals to, this equation is given, and no need to go into these details of this equation, but I am showing it here just to give you the idea that all these three noise contribute to your signal to noise ratio. Okay, and now we'll go into the details of this short noise, dark noise, and read noise. So what is a short noise? Or it is also known as photon noise. So that is caused by the random arrival of photons. Okay, since each photon is an independent event, the arrival of any given photon cannot be precisely predicted, and the probability of its arrival in a given time period is governed by the Poisson distribution. With a large enough sample, the graph plotting the arrival of photons will plot the familiar bell curve. Okay, so short noise is most apparent when collecting a relatively small number of photons. Okay, so when you are imaging the samples with a low fluorescence, at that time short noise becomes apparent. Okay, it can be reduced by collecting more photons, either with a longer exposure or by combining multiple frames. Okay, so to how you can avoid the photon noise or the short noise, either you increase your signal to noise by increasing your fluorescent light intensity or increase the exposure time. Okay, but for the low light samples, like the samples with low fluorescence, the photon noise will be visible. But if you are imaging a sample which is very bright, you cannot see, you even may not notice the photon noise. Then the dark noise. So the statistical variation in the number of electrons thermally generated within the silicon structure of the CCD. Since each photon is an independent event, the arrival of any given photon cannot be precisely predicted, and also it is governed by the Poisson distribution. And it is temperature dependent as shown below. That's why good CCD cameras are always cooled CCD. So I can show you this graph. So see, on the x-axis the temperature is there, and temperature ranges from plus 25 degree to minus 35 degree. Okay, and this is the electrons per pixel per second. How many electrons are produced because of the dark noise per pixel per second. So you can see that as the temperature goes down, this number of electrons produced are reduces. Okay, so almost if you run your camera at minus 29 or minus 35 degree centigrade, then there is no dark noise. Okay, and that's why most of the CCD camera are known as a cooled CCD. There is a thermoelectric cooling around the camera chip, and which reduces its temperature to even minus 35, or even in some cameras it can lead to minus 80 degree also. Okay, so better the cooling, you can get rid of the dark noise. The third type of noise is known as the reed noise or the pre-amplifier noise. So combination of system noise components inherent to the process of converting CCD charge carriers into a voltage signal for quantification and the subsequent processing and analog to digital conversion. So these are kind of electrons or the noise generated during the processing of photons into electrons and subsequent processing and analog to digital conversion. Okay, the major contribution to reed noise usually originates with the on-chip preamplifier. So in the next class, I will show that on the CCD camera chip there is a preamplifier. Okay, which amplifies the signal. So because of that preamplifier, there is which can lead to this reed noise. It produces some electrons which leads to this reed noise. Under the low light or low signal where reed noise exceeds photon noise, data are reed noise limited. So again, this is another type of camera noise which is mostly affected when you are imaging very low fluorescence sample. Okay, so reed noise is negligible in high signal applications. So if your signal is high, then you should not worry about reed noise. Okay, but when you are imaging the sample with low light fluorescence, then you should worry about the reed noise. Okay, so that's it about today's class, and our next class will be the on the same topic, digital images and camera technologies for microscopy. But in that case, I will show the details of CCD, EMCCD, and SCMOS camera, how the sensors are designed, and what are their advantages and disadvantages of using this CCD or EMCCD or SCMOS camera. Okay, thank you.